Alright, now we're going to go ahead and jump back into our discussion on the equilibrium constant. And there were a couple more things that we needed to go through, but I didn't want to make the video too long. So now we're back on heterogeneous equilibrium, and this is just another example of what we talked about before. Because of the fact that we have um, the reaction taking place in different phases, we have solids as well as gases. When we write our actual equilibrium expression, you notice that we're only concerned with what's in the gas phase at that point. So K equals a concentration of oxygen cubed. This is going to be a similar thing that we can look at if we only have one or two things. It makes it a lot easier for us to actually move through our equilibrium constant. Now, when the value of K is larger than 1, it's actually going to tell us a little bit of information just in the direction that K is going to go in general, will allow us to know whether it's going to be consist mostly of products or mostly of reactants. So if we have a larger value, sorry, K is larger than 1, it means that it's going to proceed as we normally would see it, or the reaction goes to completion, or it lies to the right, equilibrium lies to the right. On the other side, if we have a small value, it means that it's going to consist of mostly reactants, or the equilibrium position is far to the left, or the reaction essentially doesn't actually occur. Now, this is the first part that I was talking about as far as shifting. Based on our original values or what we have, we can determine where the reaction is going to go, whether it'll happen at all. Now, quick concept check. If the equilibrium lies to the right, I think you guys understand this one, but just in case, if the equilibrium lies to the right, that means what kind of value do we have for K? Where is it relative to 1? My hope is that as you're thinking about it, you're saying, okay, if it lies to the right, that means towards the products, that means that our equilibrium is going to be greater than 1. But if it lies to the left, that means it's going to be less than 1. Okay? Now, reaction quotient. Now, if the system isn't at equilibrium, it's useful to know, that, the direction that the reaction must proceed in order to reach equilibrium. This is going to be found by finding what we call Q. Okay? Now, to determine the direction in which a reaction proceeds, one needs to determine the reaction quotient, or Q. Q can be expressed the same way as we did K. Okay? When we're looking at Q, we're going to write it just as we did for K, but we're going to use the concentrations that we have at that time. And then understanding that relationship will allow us to see what's going to happen. Now, if Q is equal to K, that means that the reaction is at equilibrium. We have no shifting occurring. Everything is in the order that it's supposed to be. Now, if Q happens to be greater than K, that means that the reaction is going to shift to the left, consuming the products and forming more reactants until the equilibrium is achieved. Notice we said that if we've already found K, but at that time we go ahead and find Q and it happens to be larger than K, we're going to see that the reaction is going to shift to the left. Now, if K happens to be larger than Q, then that means it's going to shift to the right. And we'll go through some examples of this in class so that you can see what I mean by shift, right and left, and how we'll actually go about finding these values. Now, this is a little exercise that we're going to go through, and it's sort of to set you up on what's going to happen. We're going to introduce you to ice tables and how we'll use that to determine the equilibrium concentrations for a reaction. Now, consider the following reaction represented by the equation. We have our iron 3 ion and the thiocyanate ion going to form iron thiocyanate. Now, in trial 1, we see that we have 6 molar iron 3, a 6 molar iron 3 solution, and a 10 molar thiocyanate solution, and they're mixed. And at equilibrium, the concentration that we're dealing with overall of our iron thiocyanate is 4 molar. What's the value of the equilibrium constant for this actual reaction? Well, let's go ahead and plug in the values that we have. We know that we have 6 molar iron 3, we have 10 molar thiocyanate is going to come together to make 4 molar iron thiocyanate. So let's plug in our values. Our initial concentrations at the beginning of the reaction before anything starts, we have 6 molar, 6 moles, and 10 moles. Thiocyanate, nothing. There's going to be a change though. We know that in the end we have 4 moles, a 4 molar solution, sorry, of our thiocyanate that's actually there and waiting. Now, the shift or the change had to be the same across the board. So since we gained for a 4 molar solution here, that means that we had to lose 4 molar or 4 moles involved on the other side. That's our change, that's our shift. So initial change, so that means that equilibrium, the concentration of our iron 3 is going to be 2 moles, our thiocyanate is going to be 6 moles, and our, of course, iron thiocyanate is going to be 4 moles. We're going to take this and now plug it into our equilibrium constant. Remember we said it's going to be products over reactants. That's going to be our key. So, plugging in our value, concentration of iron thiocyanate, 4 molar, as you see here plugged in, our iron 3 times the concentration of our thiocyanate, which is 2 molar times 6 molar, and then just plug it into your calculator and solve. You should come out with an answer of approximately 0.33. Now, because the K value is less than 1, which direction is the reaction going to shift? If you said that it's going to shift left, or essentially our products, lying with our products, our reactants, you would be correct. Now, this is where we're going to end part 2 of the video. You want to go ahead and look at the information and sort of gauge where you are. If a lot of this doesn't make sense, I completely understand, and we're going to work on it to make sure that you understand what's going on by the time we get to the test date. Have a great evening, and I look forward to seeing you in class.